Today I also discuss one important topics related to measure theory, especially in LP space. We also discuss Lebesgue decomposition theorem in previous class. Okay, this one is an important theorem in measure theory. Obviously, this theorem says about that two measures here given to our sigma finite measure. Okay, and then we also find another two measure. These measures are singular with respect to some mu, that means some first sigma finite measure, and one is singular with respect to first sigma finite measure, and another one is absolutely continuous with respect to this first sigma finite measure. And then another sigma finite measure, obviously written as sum of these two measures, comma 0 and comma 1. This one is the Lebesgue decomposition theorem. You know about that. This one is too easily done. Okay, in previous class we do it, but now we also write this statement also. Okay, we also prove in previous class, but we also demonstration now. Okay, this one Lebesgue decomposition theorem. Okay, we just talk about now more. We proved in previous class, so we now talk about something about that. Which one here says? Well, I'll write this statement first. Let mu and comma. Okay, mu and comma be sigma finite measure. Be sigma finite measure. We know about that sigma finite measure equal to what? We know about that sigma finite measure equal to that means if we write this one, x equal to union of some n equal to 1 to infinity en, then obviously mu of this en less than plus infinity. Okay, and obviously gamma of this en less than plus infinity. This one is the sigma finite measure. Okay, also see about in previous classes. So well, just demonstration. Who is one? The Lebesgue decomposition theorem, one important theorem, so we have to understand about that. Okay, so we'll talk about now. Let mu and comma be sigma finite measure. Okay, so which measure is called sigma finite measure, we also talk about now. On a measurable space. Okay, on a measurable space x, this algebra. Okay, then what happened? Then there exists measures. Okay, then there exist measures gamma 0 and gamma 1. Okay, these two measures on this x close a close a script a. Okay, this one algebra. Okay, then such that what happened? First one is gamma 0 is singular with respect to this mu, first one. Okay, and second one, this one gamma 1 is absolutely continuous with respect to, okay, what, this mu. And third one is what? Third one is this gamma is equal to gamma 0 plus gamma 1, and this representation be unique representation. Okay, we also proved in previous class. Just we write the statement here and we understand about that. Okay, so what is in here? Just we take this two measure. This measure are sigma finite. We know about that which measures are sigma finite. Okay, that means some criteria involved in measures, then this measure is called sigma finite measure. And now we're getting two measures, gamma 0 and gamma 1. Okay, this gamma 0 and gamma 1 have some, that means which properties this satisfies. First, gamma 0 is also, that means find there exists. Then if this one is sigma finite measure in a measurable space, then we find two measures gamma 0 and gamma 1 on this measurable space which satisfies those conditions. This gamma 0 is singular with respect to mu, and gamma 1 is absolutely continuous with respect to mu. Okay, and then gamma we write, then another sigma finite measure is right equal to sum of these two, gamma 0 and gamma 1. Okay, understand or not? This gamma 0 is singular with respect to first sigma finite measure, and first or second, anyone you consider. That means this one is changeable. If gamma 0 is singular with respect to this one, gamma, and gamma 1 is absolutely continuous with respect to gamma, then here mu equal to gamma 0 plus gamma 1. Are you understand? Not a problem at all. So in this way we also that means understand this Lebesgue decomposition theorem. This is too easy for all, but if you remind this one is more generally, and if you remind this one for in your mind, then obviously you that means in this way you read, then this one is better for yourself. Okay, and obviously in this way you understand better. Here two measures, and with two sigma finite measure in a measurable space, then we find another two measures in this measurable space, and some these two measures, gamma 0 and gamma 1, then gamma 0 is mutually singular or singular with respect to some first sigma finite measure or second sigma finite measure, and gamma 1 is obviously absolutely continuous, same first sigma finite measure or second, anyone. Okay, then we also represent another sigma finite measure equal to sum of these two, gamma 0 and gamma 1. Too easily we also do it, and obviously this proof is too easy, I think, not hard for everyone. So we now continue further step of today. Okay, so it is that portion and going to further discussion of another portion. Okay, so which one we discuss today? We discuss one important theorem. We write it first here. Oh sorry, we write it another, gamma equal to what we define now. Let X, this algebra mu, okay, be a measure space, be a measure space. I understand this one, measure space, and if equal to x to this r plus, okay, x to r plus be a measurable function, be a measurable function, then what happened? Then obviously we define gamma e equal to what happened, integration of e f d mu. Okay, f d mu, then gamma be a measure. Okay, so we now start about that. We just written this one, this f d mu. If we write this one is better, here union 0. Okay, then we measurable function define gamma e equal to, not needed this one. Okay, if 0 added or not, then not a problem at all. So so we also discuss or define this gamma, and gamma obviously a measure. Okay, then we're going to erase that portion and going to write another theorem. Okay, or also write another theorem related to this measure space, and we also further continue today. Okay, so we write this statement of this theorem. Let mu, gamma, and lambda, okay, be the measures on a measurable space, be the measures on a measurable space, on a measurable space X, this algebra. Okay, such that what, such that first one, this gamma absolutely continuous with respect to mu, and mu absolutely continuous with respect to lambda. Okay, and second one, mu and lambda be sigma finite. Okay, be sigma finite. Then what happen? Then d gamma by d lambda equal to, here d gamma by d mu. Okay, here d mu by d lambda. Okay, then we want to going to prove of that. Okay, not a problem at all. Understand all are understand this one. I think mu, gamma and lambda be measures on measurable space xa, and such that this one gamma is absolutely continuous with respect to mu, and mu is absolutely continuous with respect to lambda. Then mu and lambda be sigma finite. Then d gamma by d lambda, or d of d lambda of gamma equal to d of d mu of gamma, or d gamma by d mu, and multiplied by d mu by d lambda, or d of d lambda of mu. Okay, so we're also going to the means proof of that. We write now here. Note that, okay, note that mu is sigma finite. Mu is sigma finite. Then what happened? Then by radon Nicodemus theorem. Okay, there exists if such that x2 of plus be a measurable function, be a measurable function. Okay, such that here gamma e equal to integration of f d mu. Okay, so for all e belongs to this algebra. Understand? I think you understand about that. Okay, so we're going to further proceed. We erase that portion and going to further. Okay, discussion of that. So erase portion and going to further discussion of that. So again by radon Nicodemus theorem we get, okay, there exists the g such that x2 or x2 0 plus infinity closed. Such that, okay, such that mu e equal to integration of, sorry, mu equal to, so not mu equal to integration of g lambda where e, okay, here e belongs to this algebra. Okay, Now let phi be a non-negative measurable simple function on x. Phi be a non-negative measurable simple function. Okay, sorry, function on x. Then what happened? Then phi equal to 1 to n. Okay, ci psi ai. Okay, where ci greater than equal to 0 and ai intersection is equal to phi, and here union of ai equal to x. Okay, then we talk about that. Here let E belongs to this algebra, then there exists E phi d mu equal to what happened? E phi d mu equal to, okay, E phi d mu equal to C summation I equal to 1 to n ci and mu of E intersection ai. Okay, then what happened? Then we erase our portion and going to further discussion of that. So we define a phi. Okay, we define a phi non-negative measurable simple functions. We also talk about in previous classes. Then phi obviously summation of I equal to 1 to n ci of and characteristics function psi ai, and ci greater than equal to 0 and ai intersection is equal to disjoint set and union of ai equal to x. Then E belongs to this algebra and integration of E here phi d mu equal to what? I equal to 1 to n ci mu of E intersection ai. Okay, then this one equal to I equal to 1 to n, okay, ci and mu of E intersection ai equal to what? Integration of E intersection ai g of t lambda. Okay, understand? Then this one equal to what? This one equal to integration of E, okay, phi g d lambda, phi g d lambda. Okay, phi g d lambda. Then what happened? Then we write about something. We erase that portion and going to further discussion of that. Since f is non-negative measurable function, since f is non-negative measurable function, okay, then there exists an increasing sequence. Then there exists an increasing sequence, okay, phi n of simple functions such that such that phi n converges to f. Okay, then what happened? Then obviously we talk about phi monotone convergence theorem. By monotone convergence theorem, we get what? Integration of f d mu here e equal to limit n tending to infinity integration of e phi n d mu. Okay, equal to what happened? But this one is too easy, I think. That means some f non-negative measurable function, there exists increasing function phi n, and phi n obviously converges to f. Then by monotone convergence theorem, this one is happen. Okay. So this one equal to what? This one equal to, we talk about here, limit n tending to infinity integration of e phi n g d lambda. Okay, that means phi n d mu equal to phi n g d lambda. We also discussed that phi d mu equal to here phi z d lambda. So in this way, phi n d mu equal to phi z d lambda. We are here, we write here phi d mu. Okay, equal to this one. So this one happen. Then what we write here? Then we talk about that if this one equal to integration of e if g d lambda. Since limit n tending to infinity phi n equal to f. Okay, so what we get here, I also erase that portion and going to further discussion of that. Okay, so when erase that portion and going to further discussion of that. This one, what we get, integration of e f d mu equal to integration of e f g d lambda. Okay, f g d lambda. Then here comma of e equal to integration of e f g d lambda, and this one equal to integration of e d gamma by d mu. Okay, and here g equal to what? D mu by d lambda. Okay, equal to d lambda. F equal to what? D gamma by d mu, and g equal to what? D mu by d lambda. Okay, then what happened? Then when next line we write about it, d gamma by d lambda, okay, equal to what? Equal to d gamma by d mu, here d mu by d lambda. Okay, so too easily we do this proof. Okay, this one chain rule. Okay, we know about that chain rule and derivative. Here this chain rule. Okay, obviously derivative with respect to measures. Okay, measure of derivative with respect to measure. This chain rule is happen. Okay, chain rule for derivative with respect to measure we also talk about now. I understand. I think not a problem at all. Okay, all I understand is too easy portion. So now we stop here. If you get this type of video, please subscribe my channel, and if you that means have any questions, comment and suggestions, please write it in comment box. And if you that means if you gives like, then please that means like this video. And so if you have some need of these videos, please subscribe my channel. Okay, so today I stop here.